Okay, so with 9.1, what we're going to be doing is, this is called integration by parts. And like I told you earlier, or like I told you Monday, integration by parts is probably one of the most important things that you need to know if you're going to have to go farther into your math career. If you're going to have to go into Cal 3, differential equations, you're going to have to be able to do integration by parts. Integration by parts is, you use integration by parts when you cannot do U substitution. So up until this point, we have figured out ways to do antiderivatives to integrate using U substitution or using little tricks that we learned in Cal 1. Well, with the problems in Chapter 9, you can't do U substitution. And so what we're going to do is we're going to learn different ways to integrate without using U substitution, but in a sense we're still going to be doing substitution. So it's just not straight up U substitution. Okay, on your formulas page, you should see this formula right here. So if you're going to integrate a function, in this case this function is called U. If you're going to integrate a function, U dv. The reason it's U dv is because you have different variables, you have different functions going on, and sometimes it looks like a product, and you know that we can't integrate products. So what you're going to do is you're going to integrate by parts. You're going to choose a U, and you're going to choose a dv. Now, some hints that you might want to remember is this. For integration by parts to work successfully, you're going to choose the dv part first, and usually that part is going to be the most complex part. And I say usually, not always. And one thing that you need to remember is when you choose a dv, it has to have an antiderivative. So if you can't find an antiderivative for your dv, you've chosen the wrong dv. Okay? So the hardest thing to do is to choose your parts correctly. And so there's some hints that you need to know in order to choose these parts correctly. First and foremost, when you choose the dv part, make sure you can integrate it. If you can't integrate it, then you've chosen the wrong dv and you need to go back and you need to fix it. Your goal when you do this is to hopefully make your integration, your integral, your function a little bit easier. In other words, if it either simplifies or stays the same, you're on the right track. If it gets harder or more difficult, you're on the wrong track. Back up and choose different parts. Okay? So what's going to happen is this, basically, is the U part is the du, and you're going to take the derivative of that.
The first one you did there, first integration of parts. There's a du is 2x dx. dv is dx dx. I guess why? I just wonder why that was.
Because when you take the derivative, you tag on the dx to tell us what we took the derivative with respect to.
Okay.
When you go backwards, because if I took the antiderivative of this right here, it'd take me to here. So here, I'm taking the antiderivative of this with respect to x. And the dx I don't need anymore. So from here, I'm going from here to here. But I could take the antiderivative from here and go back to here. It's just when you take the derivative, you need the dx, because it tells everybody what you took the derivative with respect to. Whereas if you take the antiderivative, the dx goes away because it tells everybody what you did. Anything else? All right, let's try another one. Looks about the same. see if we can do this. Walk me through it. Do you know what your parts are? Kind of the same, right? You have an x squared, an e to the 2x, and a dx, yes? What do you want to let dv be? Same discussion that we had earlier. If you let dv be x squared, the antiderivative of that's going to be 1/3 x cubed. That's horrible. That's just absolutely horrible. Whereas if we let dv be e to the 2x, what is the antiderivative of e to the u? As long as u is what? As long as u is x. It's not going to be x. So what do you have to do? We are going to let dv be e to the 2x dx. And we are going to let u be x squared. So du, this is the easy part, is going to be 2x dx. That's the easy part. Oh, why did I write? Yeah, that's fine. But how do you take the antiderivative? Let's go over here. How do you take the antiderivative? Put this over here. Right there. On your paper, it says the antiderivative of e to the u is e to the u plus c, right? But that's as long as u is just x. Because if u was just x, you just get a 1, it doesn't matter. We talked about that. We talked about that Monday. But it's not. U is equal to 2x. This should be second nature to you, when you take the antiderivative of anything that has an argument, and that argument is not just x, you have to use compensation. You have to. So the antiderivative of e to the 2x is 1/2 e to the u du, which is 1/2 e to the u, which is 2x. That should be second nature to you. As long as your argument is x, you don't have to use compensation. But if your argument is not just x, you have to use u compensation. So the antiderivative of e to the 2x, which I guess is going to be v, is 1/2 e to the 2x. Okay, now let's substitute in. So again, you should have the formula somewhere, u times v minus the integral of v du. Alright, so u is going to be x squared. V is going to be, and we're multiplying, 1/2 e to the 2x minus the integral of v, which is 1/2. I'm going to pull that 1/2 out front in a minute. We'll just leave it here for now. And then du, well, maybe I won't have to put it, is 2x dx. Why would I not pull it out? Yeah, it's going to cancel out anyway, so I'm glad I didn't do that. Alright, so we're going to have 1/2 x squared e to the 2x minus the integral of e to the 2x x dx. Did our integral get any easier? It's just like the problem before. It did get a little bit better because from our initial integral we went from x squared to our integral now we're just at an x. So here's your first integration by parts. But before we start a second integration by parts, let's check and see if we can do a u substitution. Well, if I was going to integrate x e to the 2x, or however you want to write it, you would let u be what? 2x. And when you take the derivative of 2x, what do you get? 2. But what do I need? Do you see what I'm saying? Yeah. If I have e to the 2x x dx, and I let u be my argument of 2x, then du is going to be 2 dx. Well, I can get rid of the 2 and I get 1/2 du dx. What do I need? I need an x. So u substitution is not going to work because I don't have any way of getting rid of that x. And since I don't have any way of getting rid of that x by using u substitution, that should be your bell, ding, ding, ding. What do I have to do? Integration by parts again. All right, so let's pick out a u and a dv. Same thing, u is going to be x, so du is going to be dx. And dv is going to be the same. All right, so we're going to have 1/2 x squared e to the 2x minus. Let's go again. U times v. So u this time is going to be x, and v is going to be 1/2 e to the 2x minus the integral of v du, which is dx. Now, there's a lot of cleanup we can do here. Let's write this as 1/2 x e to the 2x minus. This time I don't have anything to cancel that 1/2 out with, so let's bring it out front. So we're going to have 1/2 times the integral of e to the 2x dx. Now, I'm just going to rewrite all this down, and at the very end, can you tell me what the integral the antiderivative of e to the 2x dx? We've done it 3 times already. All right, so now let's clean up. So we have 1/2 x squared e to the 2x minus, if you want to go ahead and distribute that minus sign now, you can. I think I'm going to. 1/2 x e to the 2x, and then negative 1/2 times positive 1/2 is going to be negative 1/4, but I'm distributing a negative through, so that's going to be positive 1/4 e to the 2x. Let's see. And that's it. Questions?
I don't recall when the interval e where it's anything other than smooth and reaction is really short. You know that by heart.
We didn't make that one. We didn't make that one. Anytime you take the antiderivative of e to the anything but x, you have to use u substitution. It's just like, Chris, if we're doing the antiderivative of sine 3x. Yeah, it's the same concept as this one here. Anytime your argument of any of your trig or your natural log functions is anything but x, you have to So are you with me? Are you blown away? Are you totally confused? What? Is it getting a little bit? Are you grasping a little bit at least? Okay. It's building on a lot of Cal 1 stuff, so just get that stuff back out of the filing cabinet. Try this one. You try it. I'm going to give you a little bit of a head start. And then I'm going to catch up to you and see how you're doing. So here are your parts. You have x squared, ln x, and dx. dv cannot be what? It cannot be natural log. You cannot take the antiderivative of natural log. So, u has to be that natural log. dv is going to be the rest of it. X squared dx. So, do you remember the derivative of the natural log of x? 1 over x dx. And what is the antiderivative of v squared dx? Or, I'm sorry, x squared dx. Right? X third over 3 or 1/3 x to the third? Whatever. Plug into our formula. So we're going to have u times v minus the integral of v du. All right, so let's clean it up just a little bit. We're going to have 1/3 x cubed natural log of x minus, and I'm going to clean up this integral a lot. So we're going to have 1/3 out front. And then what can you tell me about the x to the third and the x? 1 over x. One of those will cancel out, right? So I made them 1/3 out front, and so now what I have here is x squared dx. Did our integral get better? A bunch. A whole lot better. Do you know how to take the antiderivative of x squared? Well, yeah, because we just did it. Right? We just did it to the right. So let's go ahead and do that. So we have 1/3, so we don't have to do integration by parts again because we know how to take the antiderivative of that. Oh, plus. I would have thought it was consistent. All right, clean it up a little bit. And that's all you have to do. Okay, so let's go back to chapter 8. Get your chapter 8 formula page out. For this one, you have 2 parts. You have your sine inverse x, or arc sine x, same thing. And you have dx. So we need to choose u, and we need to choose dv. And dx always goes with dv. So since dx always goes with dv, what has to be u? Because you only have 2 parts, guys. You only have 2 parts in this integral. And since dx always goes with dv, you don't have a choice. U has to be sine inverse x, or arc sine x. Don't have a choice. Okay, getting your chapter 8 cheat sheet out. Let me find it. What is the derivative of sine inverse x? You're going to have 1 over the square root of 1 minus x squared, and then times the derivative of x, which is just 1 dx. And then the antiderivative of dx, what did y'all say it was? Okay. So how did I know where to look for that sine inverse, or for the derivative of sine inverse? How did I know where to look for that? When did you learn how to take the derivative of inverse trig functions? Monday. Chapter 8. We didn't do it in Cal 1, that's for sure. We certainly didn't do it in trig because we didn't do any derivatives in trig. So it's chapter 8. Okay. Alright, so let's plug into our formula. We're going to have u, which is sine inverse x, times v, which is just x, minus the integral of v, which is x, du. Now this is where it gets a little crazy. You're going to have, our du is going to be 1 over the square root of 1 minus x squared dx. Okay, so the first part, there's nothing you can do. I mean, we can clean it up just by rewriting it, but really and truly, it doesn't do anything. Now the second one, let's think. And again, remember, we want to make this a little bit easier, okay? So, if I want to take the antiderivative of x over the square root of 1 minus x squared dx, you can look in your chapter 8 stuff because that does look familiar, right? It looks very familiar. 1 over a minus x squared. 1 over a minus u squared. 1 over a minus u squared. And so you see that that's going to be sine inverse u over a. And you can go that route, but it's not the easiest route. Because, watch this. And this is what I would always suggest. And the previous problems that we've done, I went to the u substitution first. Think about this. And this is not integration by parts again. This is Cal 1 u substitution. And I'm going to tell you why I'm doing this, okay? If I do the Cal 1 u substitution for this problem right here, and if you want to rewrite it to make it to where you can see what's going on, that's fine. What would you let u be? 1 minus x squared. So what is du? But I don't need a negative 2x. What do I need? Just an x. So by doing Cal 1 substitution, did that fix my integral? Can I integrate that? You got it right the first time. Because look, the x dx, look, right here, I can check it off. There's x dx. And what is 1 minus x squared? That's u, right? So if I have x sine inverse x minus the integral of 1 over u to the 1/2 du. Do you know how to integrate 1 over u to the 1/2 du? I hope so, because we did it multiple times in chapter 6, and we also did it in Cal 1. So, Ms. Adams, why did we not use the a minus x squared, the 1 over the square root of a minus x squared, when we could have simply just used sine inverse of u over a? Well, because we don't have 1 over the square root of 1 minus x squared. What do we have? X over the square root. So you can't do that, because there's no way for us to get rid of that x. There's absolutely no way for us to get rid of that x unless we do use substitution. And if we do use substitution, we don't even have to worry about the inverse treatment in the first place.
Why isn't the square root carried over into U substitution, and what happened to it?
Okay. It's just like if we were going to, did he answer your question?
I think so. Yeah.
Okay. It's just like if we were going to integrate something like, and we let u, we don't let u be to the third, right? We don't carry that third over there.
Okay.
So there's the x dx, so I need negative 1/2 times the integral. This is u to the third. And do you remember integrating that?
Yes. What about the half, negative 1/2 du? It doesn't go back in the other problem?
I just haven't put it in there yet. Is that better? It's actually going to go plus. Okay. Any other questions? All right, so we're doing straight. All right, so we're going to have x sine inverse. I'm done with that. You don't have to worry about that anymore. Just recopying it. 1/2 times, this is going to be u to the 1/2 over 1/2. Why did the integral symbol go away? That is the integration. That is the antiderivative. When you take the antiderivative symbol, the little s thing, goes away. So the antiderivative, you add 1 and divide by your new exponent. So if you add 1 to negative 1/2, you're going to get 1/2 and divide by that new 1/2. Now, what do we do with that denominator? Yes, you multiply by the reciprocal. What's 1/2 divided by 1/2, or 1/2 times 2 over 1? They cancel out. All right, so we're going to have x sine inverse of x plus u to the 1/2, but what is u? Okay, don't let me throw you off, okay? I'm going to change my 1/2 back to a radical. Okay with that? And I'm going to go ahead and put my 1 minus x squared back in for u. And you're done. Okay, so let's talk about this. The first part didn't change. The integration by parts, that didn't change. You got to pick out your u and your dv, okay? Once you do your integration by parts and you have a new integral, please start with your Cal 1 methods, meaning straight up integration or u substitution. If neither of those will work or nothing will come to mind, then try integration by parts again. But when you do integration by parts, make sure everything is taken care of. For example, if you wanted to use that sine inverse integral from chapter 8, you're going to have to get rid of that x somehow or another. So when you rewrite it as x over the square root of 1 minus x squared, it should be evident that you don't have that inverse sine integral from chapter 8. Because that says 1 over the square root of 1 minus x squared, not x over. So it's your substitution. It's just basically substitution. And if none of that works, then yes, you're going to have to do a second integration by parts. So what do you think? This right here is a culmination of everything that you've ever been taught. So you're just going to have to lean on it heavily. All right, let's try another one. Have plenty of examples because I want to make sure that we cover anything that you're going to see, whether it be in homework or tests for sure. Now this one's not so bad. I think you can do this one on your own. See? All right, so I'm going to catch up to you. Just keep on working, do whatever it is that you're doing. So we have your parts here. Again, you have x, sine x, and dx. So you have u, and you have dv. And you know that dx has to go with dv. So if I let u be x, du is going to be what? Just plain dx. That was easy enough, right? That's not hard to integrate dx, is it? Because do a little bit of forward thinking. Du and v are the two things that you're fixing to integrate. To integrate dx is really easy, is it not? Because that's going to be part of your new integral. The integration of dx is easy. It's just one. Actually, it is. All right, so dv, if we let that be sine x, what's the antiderivative of sine x? Can you take the antiderivative of negative cosine x? Pretty easily once you move the negative out front. What's the antiderivative of cosine x? So do you see what I'm saying? When you start choosing your parts and you come up with the du and the v, that's going to be your new integral. And if you can't integrate those two things together easily, you might want to back up and rethink what you're doing. Okay? So, u times v. So we're going to have x times negative cosine, and I'm going to clean that up, negative cosine, minus the integral of v, and I'm going to clean that up too, times du, which is dx. So let's clean it up. So we'll have negative x cosine x plus the integral of cosine x dx. So we'll have negative x cosine x plus the integral of cosine x we said was what? So they're not all boogers, right? Some of them can be fairly simple, and you're hoping and praying that I give you one of these on your test, right? But most of you see trig and you freak out, even though the trig ones are the easier ones. Okay, let's try this one. Now, do you see the parts here? Tell me one of the parts. Not labeling, just tell me the different parts in this problem. Do you see one of them? Cosine x. What's the other one? Natural log of sine x. That's the argument of your natural log. And what's the other one? Dx. All right. Now, all right, so dv cannot be natural log sine x, so that forces me to make my u natural log of sine x. And so dv is going to be cosine x dx. Can you tell me the derivative of natural log u? 1 over u, which is sine x, times the derivative of u, which is what? That's Cal 1 stuff, guys. The derivative of natural log of u is 1 over u du. And you have to use the du here because u is not x. It's sine x. That's Cal 1. And you can clean that up, and I will. I mean, you can write it as cosine x over sine x. But let me give you a little bit of a hint. Don't use your trig too quickly. Wait and see if something, because you're fixing to do some multiplication, wait and see if stuff cancels out before you use your trig identities. Yes. In other words, don't change this cosine x over sine x into cotangent x too quickly. Okay? Just be patient with it. Just be very, very patient. Okay, so v, what's the antiderivative of cosine x? Okay, let's plug in. So we're going to have u times v, and please don't put that that's the natural log of sine squared x. One's an argument, one's a product. Minus the integral of v du. And you'll see why I say don't be too quick with your substitutions. Do you see why? I had much rather cancel something out than try to take the antiderivative of cotangent. Hadn't you? I would think. I mean, I know you have your cheat sheet, but still. Alright, so let's clean it up. So we'll have sine x, natural log of sine x, minus, what will cancel out? The sine x and the sine x. So you're going to have the integral of cosine x dx. And that we can do pretty easily. Yes? What is the antiderivative of cosine x? The antiderivative of cosine x is what? Sine x? Is that right? And I'm okay with this. And I don't know what the back of the book will say. I mean, if you want to factor out a sine x and do sine x times the natural log of sine x minus 1, whatever. I don't need that dx though, do I? Okay. There's one more technique that I need to show you, and this is this problem. Sometimes, remember I told you at the very beginning when we were doing integration part by parts, I told you either one, your purpose is to make your integral easier or the same. If your integral stays the same, no matter how many times you do integration by parts, in other words, if it's looping, then you're going to have to use this technique. Okay? So just remember, if your integral does not get easier, but it stays the same, you're just doing a continuous loop, and this is what you're going to do. So here, let's start by just going ahead and doing integration by parts, just like normal. So can you tell me what the u and the dv are going to be? What do you want to try? Okay, if we let dv be cosine x dx, then the antiderivative of that is going to be sine x, which is not so bad. And if we let u be e to the x, then du is going to be e to the x, which is still not so bad, but we haven't really made any progress. So let's flip-flop it and see what happens. If we let u be cosine x, what's du? Negative sine x. And if we let dv be e to the x, what is v? E to the x. Still haven't made any progress. Do you see what's happening? No matter which way you go, it's not going to get better, but it's going to stay the same. Having said that, e to the x is never going to change. Whether you take the derivative of it or the antiderivative of it, it's never going to change. The only thing that's going to change is your trig portion. It's going to go from cosine to sine and back to cosine. Right? And that's the looping that I'm talking about. That's the looping that I'm talking about. So let's let u be cosine x. And let's let dv be e to the x dx. Alright, so du is going to be what? A negative sine x. And v is going to stay the same, basically. It's just going to be e to the x. Okay, so let's watch what happens. U times v is going to be cosine x e to the x minus the integral of v, which is e to the x, du, which is negative sine x dx. Clean it up a little bit, so we'll have e to the x cosine x plus, you know where that's coming from? Integral e to the x sine x dx. So, did our integral get any better? No, it stayed about the same, right? Can I take, doing u substitution, just going through the thought process, doing u substitution, can I integrate e to the x sine x? No, because if I could have, I would have done it initially with v to the x cosine x, right? So this is your first integration by parts. And so let's try it again, because that's just standard. Try to make your integral better by doing a second integration by parts. So if we do a second integration by parts, we got to choose another u and another dv. Don't change it up. Be consistent. So u is going to be sine x dx. No, it's not. It's going to be sine x. All right, so du is going to be cosine x, and v is going to be e to the x. Exactly. You're back to where you started from. Watch this. So we're not going to change the u times v. So you're still going to have e to the x cosine x plus. You're going to do your integration by parts one more time right here. U times v minus the integral of v du. Look, is that not what we're trying to find in the first place? Not an infinite loop, because there is a solution. If it was an infinite loop, there wouldn't be a solution. All right. Let's clean this up just a little bit. So we'll have e to the x cos. Are you kidding me? So just be aware if something continues to loop. And it takes you back to where you started from. Set your original integral equal to that very last line of your second integration by parts. Good place to make a note right there. Okay? Set your original integral equal to your second integration by parts. Set your original integral equal to your second integration by parts. And then solve the equation using algebra. Questions? All right, take a break. Be back at 5 after. And like I said, it is on the second part of your formulas page. So there are a few things that happens with these trig integrals. either one, which is the first case, which we're going to talk about, where you have odd powers of sine and cosine. That's this one. In other words, if you have something that has something like sine cube x, or maybe cosine to the 5th x, if the exponent on either your sine or your cosine is odd, you're going to use this technique. Okay? If either of your exponents on sine or cosine is odd, you're going to use this technique. And I will tell you, if there is an odd power in your problem on sine and cosine, use this technique. Because when we get into the evens, you're not going to like it at all. So if you can use the odd, by all means, use the odd. Okay, so if n is an odd integer, and we are talking about this power here. If n is an odd integer, this is what you're going to do. You're going to rewrite your integral, which is sine n or sine cosine, whatever, as take your sine and lessen it by 1, and then multiply it times another sine. Because you know sine x times sine x is sine squared x, right? So I can say, if I had something like sine cube x, that would be the same as sine squared x times sine x. You agree? Same thing. So what are we going to do? Well, when you lessen it by 1, hopefully what's going to happen is you're going to get an even substitution. And maybe you can make it into sine squared x. And that's what you want. Or cosine squared x. Because what you're going to do is you're going to use your Pythagorean. Because you know that sine squared x is equal to 1 minus cosine squared x. And you also know that cosine squared x is equal to 1 minus sine squared x. Why do we do that? Well, think about it. If we do u substitution, if we have this right here, and we do u substitution, okay? If I let u be cosine, what is du? Negative sign. Because what's going to happen, watch right here. I'm going to substitute sine squared x for 1 minus cosine squared x. And I still have that sine x in place, right? So if I let u be cosine x, du is negative sine x. Check. Because we're going to integrate. Do you see what I'm doing? So now what I have is 1 minus u squared du. Because we checked off the sine x dx. And you know where to go from here. Okay? So, if you have an odd power of sine or cosine, your ultimate goal is to pull a sine out or a cosine, depending on what your case may be, and make the remaining sines or cosines into a sine squared something or a cosine squared something. And hopefully it'll just be a sine squared or a cosine squared. But if not, that's okay. We can do the algebra. Alright, so here you have it. You have the integral of cosine to the 7th x dx. Cosine to the 7th x dx. So, what did I tell you to do? What does it say do? It says lessen it by 1, so that's going to turn into cosine to the 6th x, right? Times that cosine that we lessened it by 1. Oops. So it's going to look like this. You're going to have the integral of cosine to the 6th x cosine x. Well, you're thinking now, Miss Adams, you said that we needed a cosine squared x. Well, you do. But I can do that now. Why? And I'll show you the trick. Look, the trick is this. Your power rule from algebra. A power to a power, you multiply the powers. 2 times 3 is your 6. Okay, that's your power rule from algebra. Now, why could I not do that with cosine to the 7? What can you multiply in order to get 7? What can you multiply cosine squared by in order to get 7? What can you multiply cosine squared by in order to get 7? Nothing. Okay, so you have to get it to an even power before you can break it down even farther. Okay, so from here, what did I tell you to do with the cosine squared? What is the cosine squared going to go to? One minus sine squared, and again, we need to keep the cube in there. So why did we do this? Do you remember what I told you? Use substitution. What are we going to let u be? So what is du? Look, check, check. So the cosine x dx, that's du. That's nice. And then the 1 minus sine squared x is going to turn into u squared cubed du. Okay, so you tell me, thinking of all of your techniques from Cal 1, how am I going to integrate 1 minus u squared to the 3rd power du? What's the first thing that pops up to your head? Algebra should be the first. Remember when we do integration, your first option is to do straight up integration. We can't do straight up integration here. Your second option is to see if you can do some algebra. If you can't do the algebra, your third option is use substitution. Use substitution is not an option here because if I do use substitution, I'm going to get u is equal to 1 minus u squared. Du is going to be 2u. That doesn't help at all. So do the algebra. What is 1 minus u squared to the 3rd power? Can you do that algebra? It's going to take a while unless... Alright, so either way, hopefully you're going to have 1 minus 3u squared plus 3u to the 4th minus u to the 6th du. Can you integrate this? I hope so. You're going to integrate each one of these separately, right? Because you can integrate the sums. That's what integration is anyway. So if I integrate 1, what do I get? And we're integrating with respect to u. So if I integrate 1, what do I get? U. If I integrate 3u squared, what do I get? And 3u to the 4th. And u to the 6th turns into u to the 7th over 7. And now all you gotta do is plug in your u. Well, what is u? It's been forever since we've seen it. So we have sine x minus sine cube x plus, you can do 3 sine to the 5th over 5 if you want to, or you can pull it out, say 3/5 sine to the 5th x minus 1/7 sine to the 7th x plus c. And there's your trig. So one more time. So do you see this? One of them's even and one of them's odd. And that's why I stressed a while ago. If either one of them is odd, you want to use this technique. So as you're going through your test, as you're going through your homework, as you're studying, if either of your sine or cosine is odd, to go with that one. I'm going to pull a sign out, and I'm going to multiply it times sine squared, and then of course cosine squared is going to stay as is. What's the next step? Make your substitution. So you're going to have sine x. This is the one I'm going to substitute in for. Notice I did not substitute in for both of them. Sometimes it may be necessary, sometimes it's not. This one is not necessary. What was the next step? You did your algebra, you did your trig. What's the next step? Cal 1. Use substitution. What are we going to let u be? It's going to be what you changed in the trig part. So what's it going to be? Cosine x. So du is going to be what? Negative sine x. Now, we don't have a negative sine x, we have a sine x, but we can fix that. That's going to be negative, okay? Just pull that negative out front. So if we check off, there's dx and there's sine x. Well, what about that extra cosine u, or cosine squared x? It's u. What is u? Cosine x. So the sine x dx turned into du. Everything that I checked off in red, that's du. It's gone into the du. Okay? 1 minus cosine squared x is going to turn into 1 minus u squared, because cosine x is u. And then that other cosine squared x is also u squared. Okay, we did algebra, trig, cal 1. Algebra, trig, u substitution. Do the u substitution on the trig that you substituted in for. Okay, that's the whole purpose of doing it. Now let's go back to cal 1. We need to integrate this. Can you integrate it straight up? No. Can you do some algebra to it? Sure. Let's do some algebra. This is just the distributive property, right? Can you integrate that straight up? Yes, absolutely. When I integrate, I'm going to go ahead and take the negative sign in. I hope that's okay. And then the last step, what do we need to do? Substitute back in for u, right? So u, we said, was, and again, how you write it is completely and totally up to you. And so you have negative cosine to the third x over 3, and negative cosine to the fifth x over 5, or you can write it like I did on the board. It's completely and totally your choice. Okay, so what happens if we have even powers? What happens if we have even powers? Well, you know if you have the cosine squared or the sine squared, you already know what to do with that, right? We just can't do that. If you have an even power, then we're going to use the half angle identities from trig, the half angle identities. So if you have a sine squared x somewhere, you can substitute in 1 minus cosine squared x over 2. Or if you have a cosine squared x, it's 1 plus cosine squared x over 2. Number one mistake, and I don't know why this happens, because you have your cheat sheet in front of you, you have your formulas page in front of you, but for some reason or another, people are just going along and thinking I don't need to look at my formulas page. And for the sine squared x, you'll put 1 minus cosine 2x over 2. But then for the cosine squared x, you'll put 1 minus sine squared x over 2. make sure you use what you're given. Now, disclaimer, only do this if there are no odd powers in your original problem. If there are odd powers in your original problem, use the odd technique because it's so much easier. And when we do one of these, you'll understand. It is so much easier to do the odd than it is to do the even. Now, a couple of things that I need to show you is this, because I'm going to be using all of these so that when I write them, I don't want you to be confused. Okay? 1 minus cosine 2x over 2 can also be written as okay, you're just putting them together or taking them apart. And it can also be written like this. Okay, and the same on the right. And I'll be using whichever one works for me in that particular problem, that's the one I'm going to use. It's just algebra. So I shouldn't think that it should throw you off too badly. But I just want to give you a heads up as to, so that later on you won't be like, whoa, where did this come from? And I will tell you, this shows up in Cal 3. When we start graphing the cardioids and the fine graphs, this will come up. Okay, so please remember this for Cal 3. Don't get in the Cal 3 class, whether it be here or at university, whatever. Don't get in the Cal 3 class and act like you've never seen this. I'm begging you. At least say, oh yeah, I kind of remember that vaguely. Whether you know it or not, at least know in your head, oh yeah, I remember doing that. Right. Okay, so let's look at this one. If you have cosine to the 4th of x, now what we can do here is we can make this into the integral of cosine squared x squared. All right, so anyway, we have cosine squared x squared. Why, right here, why can I not do what I did earlier? Why can I not change that cosine squared x into 1 minus sine squared x and use u substitution? Because if I let u be cosine squared x, du is, or cosine x, du is going to be negative sine x. I don't have a negative sign to check off. Do you understand that? That's why we're having to change techniques. Because I don't have a sign in there to check off anywhere. Okay. Or, why can't I say something like cosine to the 3rd x times cosine x? Break it apart like we did with the even power, or with the odd powers. Now I have an odd power, and I can go again, and I can say, oh, well, I can say that's going to be cosine squared x times cosine squared x. You're chasing your tail at that point. Okay? So, let's move forward, not backwards. All right, so we have cosine squared x, quantity squared, which is going to give you your cosine 4x. That's algebra. From here, let's go ahead and do the trig substitution. Cosine squared x, quantity squared is going to be what? 1 plus cosine 2x over 2, and we are going to square it. Now, I don't know, the problem is, we're going to go to Cal 1 now. The problem is I don't know how to integrate a fraction. Algebraically speaking, however, I can fix this fraction. Because that fraction can be made into a constant. Watch this. Don't let me lose you on this. and this is the way I like to do it. If you want to do it a different way, that's fine with me. But the way I like to do this is, watch. Remember a while ago when I did this? Now, I can pull the 1/2 out. It is and I need you to understand this. I really need you to understand this. I can pull that 1/2 out as a constant, but it's not going to be 1/2, it's 1/2 squared. Do you see that? So in all actuality, I'm going to be pulling out a what? 1/4. And that's going to leave me with 1 plus cosine 2x squared dx. And the fraction's gone. Now this is what I need you to understand. The 1 that's left in there, I have to integrate that 1. It's not a constant that I can pull out. Do you understand why? It's in a group with that cosine x. That's why you can't pull it out. We learned that in Cal 1 vaguely, if you kind of sort of remember it. Okay? So now we have 1/4 times the integral of 1 plus cosine 2x quantity squared. Where do you want to go from here? Think about our techniques. We did algebra, trig, a little more algebra. What can we do with this 1 plus cosine 2x quantity squared? We can do some more algebra, can't we? We can do some more algebra. So we're going to have 1/4 times the integral. Do you remember the pattern for this? A binomial squared is what? Square, double square, very good. So we're going to have 1 plus 2 cosine 2x plus cosine squared 2x dx. All right. I know how to integrate two of the 3. Can you tell me which 2 I know how to integrate? You know how to integrate 1, yes? 1 dx. That's just going to be x. Do you know how to integrate 2 cosine 2x? Use substitution. Because it's not just cosine x, it's cosine 2x. So you're going to have to use substitution. U is going to be 2x, so you get 1/2 cosine 2x, which is going to ironically cancel those out. But what about the cosine squared 2x? What do you think? Look at the very first line that we wrote. You have it again, don't you? Well, initially we had a cosine squared x, but now we have a cosine squared 2x. Concept's still the same. You have a cosine squared. When you have a cosine squared or a sine squared, you have to use those identities. You have to use those half-angled identities. When you have a cosine squared or a sine squared, you have to use those half-angle identities. Unless you have something else in there that you can do use substitution to check off, and we don't. That would be going back to the first examples that we did. Okay, so let's fix this. So we're going to have 1/4 times the integral. Notice I'm not going to do any integration until I have it simplified as far as I can. Now this is going to turn into, well, I don't know how I want to write it just yet, so we'll just do it this way. 1 plus, now, watch this. You might want to make a note of this on your paper or in your notes. If cosine squared x is 1 plus cosine 2x over 2, what do you think cosine squared 2x? What are you doing with the angle? 4x over, it's still going to be 2. 4x over 2. 4x over 2. Dang, I'm going to have a fraction again. That's just a pain in the hind end. But we can fix it. Can we not? Let's see what we want to do here. We have 1/4 times the integral of 1 plus 2 cosine 2x plus. How did we write it a while ago? 1/2 plus 1/2 cosine 4x dx. Is that the same thing? That's one of the ways that we wrote it a while ago, right? There's one other thing that I want to do to simplify before we integrate. Can you tell me what it is? Add the 1 and the 1/2. Those two are constants. I can add these together. All right. So one more time. We're going to have 1/4 times the integral of 3/2 plus 2 cosine 2x plus 1/2 cosine 4x dx. All right, so let's integrate. So we're going to have 1/4 times. What's the integral of 3/2 with respect to x? 3/2 x, very good. Plus, what's the integral of 2 cosine 2x? You want to go off to the, okay. So off of our scratch paper, we integrated the 2 cosine 2x, and we came up with what? Sine 2x. Plus, see if you can integrate 1/2 cosine 4x. See if you can do it in your head. You should be getting there if you're not there already. We know the antiderivative of cosine is sine, so that's the easy part. But we don't have u. We don't have just x. We have 4x. So u is going to be 4x. So du is going to be 4 dx. But I have to use a 1/4 compensation. What am I going to do with that 1/4? Multiply it times the 1/2 that's already there. So you should be coming up with 1/8 sine 4x. Okay, so that's all the integration. Now let's take the 1/4 and multiply through, so that's going to give us 3/8 x plus 1/4. Okay, so we have 1/4 sine 2x plus, what, 1/32 sine 4x plus c. Now do you see why I say if there's an odd, use the odd? Because the evens, they're not that bad. You have to be patient. And you have to pull on a lot of math background. A lot of math background. So, I mean, expect one of these on your test. Just one, though, because it will take forever. But yes, definitely expect one of these on your test. All right, the last thing we're going to talk about, so we're not going to make it to 9.3, unfortunately. I know that just breaks y'all's heart. 9.3 is actually the easiest of the ones tonight, but I can't make it. I just can't. Okay, so the last one that we're going to talk about on your cheat sheet is the powers of tangent and secant. And it goes back to your trig identities. So, of course, your goal is to get either tangent squared or secant squared. Okay? So, again, that's your Pythagoreans, some more of your Pythagoreans. And there's 3 different cases. Case number 3, I will not give you, but it's out there just so you know. Case number 3 says if the power of tangent is even and the power of secant is odd, there is no method to evaluate. There's no solution. It can't be evaluated right now. tangent is odd, and that's all that matters. If the power of tangent is odd, look at what you're going to do. You're going to save a tangent secant, and that should be obvious because if you go back to your Cal 1 or the inside front cover of your calculus book and do a little bit of forethinking, what's the derivative of secant? What's the derivative of secant? Secant tangent. So, if the power of tangent is odd, you want to save a tangent secant or secant tangent. Those are interchangeable because it's multiplication. Save that for when you do the derivative of secant. You should be thinking that. If I'm saving a tangent secant, there's a reason. Somewhere down the line, u is going to be secant. And if u is going to be secant, then the derivative of secant is tangent secant or secant tangent, either way. Okay. Convert the remaining even power of tangent into hopefully a tangent square. You need to get it into a tangent square, just like we've been doing all night long. Once you get it into tangent square, that's the algebra. Now use your trig identity and substitute secant squared minus 1. Then use your calculus with u substitution. U is going to be your secant x. Du is going to be your secant tangent that we saved out earlier. And then go with your u substitution. That's case 1. Case 2, if the power of secant is even. If the power of secant is even, save a secant squared. Reason being is because converting the remaining even power of secant into a secant into a different secant squared. And then using your trig. Because look on your trig sheet, or not your trig sheet, but your Cal 1 sheet. What's the derivative of tangent x? Tangent u? Secant square u. So do you see how they go hand in hand? Do you see how they play off of each other? Okay. So, again, case 2, if the power of secant is even, you want to save out a secant square for the derivative of tangent, and you want to make the remaining into a secant square so that you can use your trig. All right, so let's work on this. So here we have secant to the 6x dx. Secant to the 6x dx. Which case do we have? Case 1 or case 2? We have case 2. What does it tell you to do? It says to save a secant squared x, does it not? Well, if I pull out a secant squared x, according to algebra, what can I multiply to get my original problem? Right? Do we get that? That's multiplication. Secant squared times secant to the 4th is secant to the 6th, right? But, look at case 2. If the power of secant is even, then save a secant squared x. We did that. We pulled out a secant squared and we were left with secant to the 4th. But then it says convert the remaining even power of secant into something like that. Can we do that? We did it earlier. We did it earlier with our sines and cosine. Can you tell me what I'm going to make that secant to the 4th into based on our earlier work? Do you remember doing that? Okay, so all the algebra's done. We have it set up the way we need it. We saved the secant squared x, and then we converted the remaining secant into some form of secant squared x. In this case, it was secant squared x quantity squared. Next step, what do we do? Trig. Which one am I going to substitute in for? The one in parentheses. That's the one you're gonna substitute in for. So we're gonna leave this one as is. This one's gonna go into, what is that identity? 1 plus tangent squared x. So there's your trig. Let's use some calculus. What is u going to be? What is du? Watch this. Watch. There's dx, and there's my secant squared x. So what do I have? 1 plus, what is tangent x? U, but it's squared, right? And then squared, du. Where do I go from here? Algebra. Square double square. So we're going to have 1 plus 2u squared plus u to the 4th du. Where do I go now? Integration. Integration with respect to u, so the integral of 1 is just going to be u. The integral of 2u squared is going to be 2u to the 3rd over 3. The integral of u to the 4th is going to be u to the 5th over 5 plus c. Nothing's going to cancel out, so all I've got to do is substitute back in for u. What is u? Tangent x. So we're going to have tangent x plus 2/3 tangent cube x plus 1/5 tangent to the 5th x plus c. So it's kind of like what we've been doing. It's just using a different trig identity. It's using a different trig identity. Steps are the same, thought process is the same, and the setup is the same. You're just using a different trig identity. Okay, tell me what I have here. Which case do I have here? Case 1 says tangent is odd. Case 2 says secant is even. Which one do I have? Case 1. Case 1. All right, so case 1, what do the instructions tell me to do? First thing I'm going to do is save a tangent x secant x. We're doing algebra here, so if I multiply tangent x secant x times what to give me tangent 5x secant x? That's all I need, right? I pulled out a tangent secant, which is going to lessen those 5 tangents down to 1, and the secant came out. So I have tangent x, secant x, tangent 4x. And please understand this is all multiplication. Okay? It's tangent x times secant x times tangent to the 4th x dx. Now what? What does it say do with the remaining tangent x, even power x? And we've done this twice already, so what is this going to turn into? So that's algebra. What's our next step? Nope, not use substitution. Because we don't. If we let u be tangent, what's the derivative of tangent? Secant squared. We don't have anything to take off. Trig. You got to use your identities. So this is going to turn into tangent squared x is going to be secant squared x minus 1 squared dx. Okay, algebra, trig. Now what? Now you're going to do your u substitution. What is u going to be? Secant x. And the whole point of all the algebra and trig is this right here. Because when I take the derivative of secant, what do I get? Secant x, tangent x. And that can be written as tangent x, secant x. So, watch. Check the dx. Check the secant. Check the tangent. So what's left? What's left? u squared minus 1 squared du. Because secant is u, right? And it's squared. The minus 1 is tagged in there. That's squared. Where do we go from here? Algebra. Algebra. So we're going to do square, double, square. Not plus c just yet. Jumping the gun. Alright, so Jiminy Crickets. Let's do u, not this. Integrate. So we're going to have u to the 5th over 5 plus 2u to the 3rd over 3 plus u plus c. Substitute back in, so we're going to have what? 1/5 secant to the 5th x plus 2/3 secant to the 3rd x plus secant